Hello everyone, welcome to the online lecture series of the course EE204 Digital Electronics and Logic Design. Module 5 Synchronous Counters and State Machines. We all know that a counter is a device which is used to count how many times a particular event has occurred electronically. Basically, the counters are classified into two asynchronous counters and synchronous counters. We have already seen in detail the asynchronous counters. Now we are going to study in detail about the synchronous counters. Synchronous counters are counters in which all the flip-flops are triggered simultaneously, that is in parallel by the clock input pulses. Whether a flip-flop changes its state or not depends on the flip-flop's inputs, that is JK, D, T or SR. Since all the flip-flop changes state simultaneously in synchronization with the clock pulse, the propagation delays of flip-flops do not add together as in ripple counters to produce the overall delay. Here, the propagation delay of a synchronous counter is equal to the propagation delay of just one flip-flop and the propagation delay of the gates involved, if any. Hence, the synchronous counters can operate at much higher frequencies than those that can be used in asynchronous counters. A synchronous counter can be preset to any desired starting count either. Next is preset and clear modes. The preset and clear modes of a flip-flop works with the asynchronous inputs of the flip-flop. We have already familiarized with the asynchronous inputs, that is the preset and clear asynchronous inputs. A flip-flop input can be synchronous inputs or asynchronous input or clock signal. Synchronous inputs are those inputs to a flip-flop which will change the output of flip-flop with respect to the clock signal, whereas asynchronous inputs are those inputs which will change the flip-flop output irrespective of the clock signal. They can change the flip-flop output instantaneously. Usually, the asynchronous inputs are available in two formats for a flip-flop: active low asynchronous input and active high synchronous input. Active low asynchronous input, the preset and clear function will be obtained upon giving a low signal to that pin, and their normal resting values will be logic high. Similarly, for an active high asynchronous input flip-flop, the preset and clear function is obtained by providing a high signal to the pins, whereas the normal resting signal value is logic low. Next is synchronous counter synthesis. A synchronous counter is a counter circuit in which all the flip-flop will be provided with the clock signals simultaneously. Since the clock signals are obtained simultaneously, the flip-flop output will be depending upon the synchronous inputs of the flip-flop. So in order to make required output of the flip-flop, we need to provide proper set of input signals. So in order to decide the proper input for the required output of a flip-flop, some logic circuitry must be used along with the flip-flops. Basically, we can divide the design procedure of a synchronous counter in 5 steps. In the first step, we need to obtain the number of flip-flops required for the circuit. So we can use the relation the number of states n less than or equal to 2 raised to n, where n is the number of flip-flops. The next step is to draw a state diagram, and based on that we have to prepare a table showing the present state and next state of each of the flip-flop outputs. In the third step, we need to complete the inputs of each of the flip-flops by comparing the present state and next state, and also using the excitation table of the flip-flop which is required for your circuit. In step 4, we'll be using the table entries of each flip-flop input to populate the K-map, and by simplifying the K-map, we can obtain the minimal Boolean expression for each of the input. In the last step, these Boolean expressions obtained in the previous step are used to implement the logic circuit diagram. A sample of the design table is given at the end of this slide. Here, we are assuming that Three number of D flip-flops are required for your circuit. We are naming the flip-flops to be A, B and C. So correspondingly, the flip-flop outputs in the present state are denoted by QA, QB, QC, and the flip-flop output in the next state are denoted by QA plus 1, QB plus 1 and QC plus 1. A similar kind of table must be prepared during the step 2. We will see the detailed procedure in the following examples that we'll see in the next lecture.